Hello, everybody. We're just going to have a little chat about AI things. Hopefully, you'll find it interesting. So, Yann, there's been a lot of interesting things going on in the last year in AI. What has been the most exciting development, in your opinion, over the past year?
Too many to count. But I tell you one thing, which may surprise a few of you. I'm not so interested in LLMs anymore. You know, they're kind of the last thing. They are in the hands of, industry product people, kind of, improving at the margin, trying to get, more data, more compute, generating synthetic data. I think there are more interesting questions in four things. How you get machines to understand the physical world, and Jensen talked about this this morning in this keynote. How do you get them to have persistent memory, which not too many people talk about? And then the last two are, how do you get them to reason and plan? And there is some effort, of course, to get LLMs to reason. But in my opinion, it's a very kind of simplistic way of viewing reasoning. I think there are probably kind of more better way of doing this. So I'm excited about things that a lot of people in this community, in the tech community, might get excited about 5 years from now. But right now it doesn't look so exciting because it's some obscure academic paper.
But if it's not an LLM that's reasoning about the physical world and having persistent memory and planning, what is it? What is the underlying model going to be?
So a lot of people are working on world models, right? So what is a world model? A world model is, we all have world models in our mind. This is what allows us to kind of, manipulate thoughts, essentially. So, we have a model of the current world. You know that if I push on this bottle here from the top, it's probably going to flip, but if I push on it at the bottom, it's going to slide. And, if I press on it too hard, it might pop. So we have models of the physical world that we acquire in the first few months of life, and that's what allows us to deal with the real world. And it's much more difficult to deal with the real world than to deal with language. And so the type of architectures that I think we need for systems that really can deal with the real world is completely different from the ones that we deal with at the moment, right? LLMs predict tokens.
Right, but tokens could be anything. I mean, so our autonomous vehicle model uses tokens from the sensors, and it produces tokens that drive. And in some sense, it's reasoning about the physical world, at least where it's safe to drive and you won't run into poles. Why aren't tokens the right way to represent the physical world?
Tokens are discrete, okay? So when we talk about token, generally we talk about a finite set of possibilities. In a typical LLM, the number of possible tokens is on the order of 100,000 or something like that, right? So when you train a system to predict tokens, you can never train it to predict the exact token that's going to follow a sequence in text, for example. But you can produce a probability distribution of all the possible tokens in your dictionary. It's just a long vector of 100,000 numbers between 0 and 1 that sum to 1. We know how to do this. We don't know how to do this with video, with natural data that is high-dimensional and continuous. And every attempt at trying to get systems to understand the world or build mental models of the world by being trained to predict videos at the pixel level basically have failed. Even to train a system like a neural net of some kind to learn good representations of images, every technique that works by reconstructing an image from a corrupted or transformed version of it basically has failed. Not completely failed, they kind of work, but they don't work as well as alternative architectures that we call joint embedding, which essentially don't attempt to reconstruct at the pixel level. They try to learn a representation, an abstract representation of the image or the video or the natural signal that is being trained on, so that you can make prediction in that abstract representation space. The example I use very often is that if I take a video of this room and I kind of pan a camera and I stop here and I ask the system to predict, what's the continuation of that video, it's probably going to predict there's a room and there's people sitting, blah, blah, blah. There's no way it can predict what every single one of you looks like, right? That's completely unpredictable from the initial segment. of the video. And so there's a lot of things in the world that are just not predictable, and if you train a system to predict at the pixel level, it spends all of its resources trying to come up with details that it just cannot invent. And so that's just a complete waste of resources. And every attempt that we've tried, and I've been working on this for 20 years, of training a system using self-supervised learning by predicting video, doesn't work. It only works if you do it at the representation level. And what that means is that those architectures are not generative.
You're basically saying that a transformer doesn't have the capability but people have vision transformers and they get good results.
That's not what I'm saying, because you can use transformers for that, right? You can put transformers in those architectures. It's just that the type of architecture I'm talking about is called JEPA, Joint Embedding Predictive Architecture, right? So take a chunk of video or an image or whatever it is, even text, run it through an encoder, you get a representation, then take the continuation of that text, video, or transform version of the image, run it through an encoder as well, and now try to make a prediction in that representation space instead of making it in the input space. Right?
You can use the same training methodology where you fill in the blanks, but you're doing it at this latent space rather than down in the raw representation.
Exactly. Yeah. And the difficulty there is that if you're not careful, if you don't use kind of smart techniques to do this, the system will collapse. Basically, it will completely ignore the input and just produce a representation that is constant. It's not very informative about the input. So you have to, and until 5-6 years ago, we didn't have any technique to prevent this from happening. So now, if you want to use this for an agentic system or a system that can reason and plan, then what you need is this predictor, which, when it observes a piece of video, it gets some idea of the state of the world, the current state of the world. And what it needs to do is being able to predict what is going to be the next state of the world, given that I might take an action that I'm imagining taking. Okay. So what you need is a predictor that, given the state of the world and an action you imagine, can predict the next state of the world. And if you have such a system, then you can plan a sequence of actions to arrive at a particular outcome. And that's the real way that all of us do planning and reasoning. We don't do it in token space. So let me take a very simple example, right? There's a lot of so-called agentic reasoning system today. And the way they work is that they generate lots and lots and lots of sequences of tokens using sort of different ways of generating different tokens stochastically. And then there is a second neural net that tries to select the best sequence out of all of the ones that are generated. It's sort of like, writing a program without knowing how to write a program. You write kind of a random program, and then you test them all, and then you keep the one that actually gives you the right answer. I mean, it's completely hopeless.
Well, there's actually papers about super optimization that suggest doing exactly that.
Right.
For short programs like.